Assalamualaikum warahmatullahi wabarakatuh. So today we will explain the PID controller design for speed control system. We are from Group 4, consist of Chai Chun Kang, Ilmi Abdul Hakim, Muhammad Shami, and Ahmad Miyakini. So the abstract of this research is the importance of maintaining correct water levels in tanks or container in various applications. We also prepare the proposal of PID-based controller system for water level control using a DC motor pump. Utilization of simulation tools to showcase the accuracy and precision of the PID-based control system. So the effective maintenance of the desired water level by adjusting the speed of the water pump.
In this project, the problem statement, we need to basically design the PID control system for the water level inside a tank. These are the parameters given for everything. And also, here is our block diagram for the system of that we want to create. Here we have the Laplace transformations. We have equation 1, equation 2, 3, 4. And then from 3 and 4, we can get equation 5. From there, we can grab all of our substitutions into this form, in which we can then rearrange into our transfer function. After that, we can find the total moment of inertia and also the viscous friction to get J and B in order to input it into our transfer function, and finally getting our final transfer function, which is this one. And then after that, we can get the magnituding of PID gain using the Ziegler-Nichols method, which is right here. We can grab the S3, S2, S, and the no S. These are the poles. And then after that, we can do the stable. For the stable system, we let it go into 0, and then we can basically get the K, which K critical is 118.4898. And from there, we can also grab the period of oscillation, which is PCR, which is 1.13776. And then from everything, we have the KCR and PCR. We can now find the PID of KP, TI, KI, TD, and KD using just the formula of basically the Ziegler-Nichols method. 0.5, 0.45, these are all formulas, basically grabbing the PID controller for the manual tuning. And then here we have the simulation for our control system. I will go into depth in the next part. So now let's go over to the simulation. Hello, my name is Ibn Abdul Hakim bin Zahruddin with a matrix number of AE20037, and I will be explaining to you about our problem statement, also about our manual calculation, and our block diagram and graph of our control system of the water level system. In this project, the problem statement, we need to basically design the PID control system for the water level inside a tank. These are the parameters given for everything. And also, here is our block diagram for the system of that we want to create. Here we have the Laplace transformations. We have equation 1, equation 2, 3, 4. And then from 3 and 4, we can get equation 5. From there, we can grab all of our substitutions into this form, in which we can then rearrange into our transfer function. After that, we can find the total moment of inertia and also the viscous friction to get J and B in order to input it into our transfer function, and finally getting our final transfer function, which is this one. And then after that, we can get the magnituding of PID gain using the Ziegler-Nichols method, which is right here. We can grab the S3, S2, S, and the no S. These are the poles. And then after that, we can do the stable. For the stable system, we let it go into 0, and then we can basically get the K, which K critical is 118.4898. And from there, we can also grab the period of oscillation, which is PCR, which is 1.13776. And then from everything, we have the KCR and PCR. We can now find the PID of KP, TI, KI, TD, and KD using just the formula of basically the Ziegler-Nichols method. 0.5, 0.45, these are all formulas, basically grabbing the PID controller for the manual tuning. And then here we have the simulation for our control system. I will go into depth in the next part. So now let's go over to the simulation.
I'll be presenting for the implement PI, and PID controller using PID gain from Turbo 1 system without using controller in Simulink. So first we open the Simulink, and there are various components that we are using. For example, we are using display. You can just double click and type the display, and you can find it here. Also, this is the step signal. You can just type it, or if it doesn't show up, you can find it at the library browser and type math. And you can click math operations. You can find all the we are using display. We can find the sum, and this is the integrator. This is the derivative, and this is the gain. This is the sum. This is the transfer function. This is also a transfer function component, and this is the display. This is a multiplexer, and this is scope that we are using to observe the graph response. All of the component we can get it from the math operations. So for the first, we are running a simulation using P controller. So for the I, this is the P part, this is the I part, and this is the D part. So together forming a P, I, and D part. So for the first, using P controller, so we are using A type 0 for the I and D parts, and the value for the step signal is step 1 is 1, and the final value is 60. And this is the integrator. We are using the constant. We are not changing anything. Also as the derivative, we are not changing anything. So this is the transfer function. We get it from the 0.1 to 1 and 11.2. We can get it from the question, which is the electric resistance and the electric inductance. And for the this part is the moment of inertia of the load and the plus of the moment of inertia of the rotor. So together is 0.444. And the 0.008 is a sum of motor viscous friction constant and viscous friction between both stem and plug. So after we insert the parameters, we can run the simulation. So we are using 250 for the P, so we can observe the overshoot and the steady state. So we can observe that this is the overshoot. After it overshoot, it cause the overshoot, it enter the steady state. So it's the graph response. It's the graph response for P part. And after that, we enter the value of the gain that we are obtained by the manual. So this is the value for the P part and I part. So this is the controller for PI. So we observe. So this is the graph response for controller P with I. So after that, we for the last part, which is the PID part, we enter the value. So for the PID, this is the KI. Gain 1 is 71.09388. Gain 2 is K, which is K. This is KP. This is KI, which is 124.97166. And this is the KD, which is 10.11097. After we insert all of the parameters, we run the simulation. So this is the graph for the PID response. So we can see that, we can observe that the output of the PID is much more stable. It doesn't cause any overshoot, and it doesn't. It's also enter steady state, and so it observed that the PID is the most stable rather than the P or PI. So that's all from me for the simulation tasking. Thank you.
Today I'm going to show you how to do the automatic tuning PID controller response block diagram in MATLAB. First of all, we need to use Simulink to construct the block diagram for the automatic tuning. First of all, we click on library browser and we take out all the components we needed, such as step, gain, so we will be using 2 gain, and then this one we don't need to set, and for the gain we need to set to 60 according to the instructions and manual calculations. So we take out some. So for this one we need to change the sign plus minus. Okay, next we need a PID controller. We need a PID controller, and then we need a function. We need 2 transfer functions. One is for transfer function, one is for water tank. And last but not least, we need scope for visualizations of the oscilloscope. And we start to put in the values in the transfer functions. So before that, first of all, we insert the functions in the transfer functions according to the manual calculation we obtained, which is this one, 1.28. Then for the numerator, we got 1.28. For the denominator, got 4 variables, S3, S2, S, and 0. So for the first one, we key in the values 0.05375. The next one is 4.97322. Last but not least, 1.6392. Then 0 at the end. Then we click OK. So this is the transfer functions. To show the transfer functions in the transfer function, we just drag and show. This one is water tank. So for the water tank, got its cells functions, which is 1 for the numerator and denominator is 3.142 and 0.222. So this is the functions for the water tank. Click OK. Set up the before we set up the PDI, connect them all together. And then we label each of them. Show block name game 1. This is PID controller. This is sum. This is gain. This is step. Then this is scope. See, this is the block diagram for the automatic tuning controller in MATLAB. So next we need to set up the PID value. So to set up the PID value, we need to refer to the manual calculation. So the PID value, first of all, is internal, and then tuning function base, correct. Okay, we need to set the PIDN value for the PID controller. So the PIDN can be obtained from the manual calculations. Here, PID controller gain from manual tuning. However, I got constructed tables to easy visualization for the value. So we insert the manual calculations inside the PIDN value. For the first one, P is equal to 71.197. For the I is 125.226. For the D is 10.1200. The N is 266.xx75. After that, we click OK, and then we want to tune. Before we tune, we might need to run to see got problem or not. Okay, so after running, we can know that this diagram is okay. Now we will go on, click on the PID controller to show the tuning. So after we tune, wait for a while. Okay, this is the diagram. This is the first diagram we obtained in the tuning. So we click on options, and then we show block response. For balance, update the block. Okay, so this is the first graph we obtained in the automatic tuning PID controller. So with the showing of block response and the design is focused on balance. This is the first graph. We can notice that the amplitude will reach above 1, nearly approximate to 1.1 value, and then we will start to decrease and maintain constant towards 1. If we click on reference trackings, okay, there is another graph we obtained in the PID controller auto tuning. So of course we update the block, and then we get another graph. So this is the second graph for the automatic PID controller tuning. The graph is almost the same. Also for the amplitude, is reached about 25 seconds. It will reach to value 1, and then we will maintain constants towards 1. So this is the second graph. So we can show the parameters for tune and block. So this is control parameters is table 2, performance and robustness is table 3. So as you can see, for the table 2 control parameters for tune and block, For the PIDN values are exactly the same. So for the P is 0.0006282. For the I is 6.7727 to the power of -7. So for the D is 0.00900. For the N is 14.3051. This is the table 2. So for the table 3, performance and robustness, the tune and block are the values for tune and block are also the same. For the rise time, settling time is 1.13 and 6.2 respectively. For the overshoot is 2.13%, peak is 1.02, gain margin is 39.5, phase margin is 69 degrees, and most importantly for tune and block, the closed loop stability is very good. It is stable for both tune and block. So this is the end for the automatic tuning. So we close and we take a look on our report. So first of all, we have shown that the auto tuning response diagram is the same, is working. And then for the PID tuning gain, we can click on the PID controller, and then the value gain here is the same. So I construct a table. This is for manual reading that we have inserted in the PIDN. After we auto tune, the values has changed and become, for the P it becomes to 0.006272. For I it becomes to 6.7574 times 10 to the power of -7. And then the D will become to 0.008984, and the N will become to 14.3. So it's the same. After that, we take the table 2 already explained, table 3 also, and then the graph, the two graph also explained in the PID controller after we tune in the PID controller. So this is the graph for 2. So it's the same with the report. So that's it for the auto tuning response diagram in MATLAB. So it's very easy because we just take the manual calculations and we put inside the PID controller, like in here, and then we tune, we get two graphs and the parameters. And then the scope, we can see the oscilloscope graph. So that's all from me. Thank you.
In conclusion, the study is demonstrated the effectiveness of PID controller design for water level control by regulating the speed of DC motor water pump. So these simulation tools were used to showcase the accuracy and precision of PID-based control system. The importance of water level control system in various sectors was highlighted along the examination of different control methodologies such as PID control and fuzzy logic control. So the system modeling and analysis using tools like MATLAB and Simulink were emphasized. The manual and automated tuning methods for the PID control were explored, with the automated tuning showing improved performance and reduced coefficients. So the proposed PID control design offers an efficient approach for maintaining accurate water level in control system. Further research and testing are recommended to validate the effectiveness of the PID control design in real-world applications. That's all from our group. Thank you.